Gaan we nu beginnen. Good day, everybody. We're here at a webinar of the novel elements in the second generation of Eurocode 7 ground properties, organized by the ISS MGE, SC7 and NEN. And this is already the 7th webinar of the Eurocode 7. These are all the webinars we already have had. And this time we will be talking about ground properties. And there's a lot of interest for all our webinars. As you can see here, last Monday, there were already 1,300 registered attendees and over more than 91 countries. So that's a lot. And maybe today I heard we already have 1,389 attendees. I hope the next webinars in 2024 will be about the same amount. That would be nice. Looking at the program for now, I will do the introduction, and I am the secretary of SC7. My name is Geert Kraaiema. The next presentation will be by Hakan Garin. He will introduce the Eurocode 7 Part 3 ground properties. After that, there will be Sebastiano Foti. He will talk about state stiffness and dynamic properties. Then followed by Marcos Arroyo. He will be talking about strength properties. And then examples and correlations by Kees-Jan van der Made. All our speakers are experts on their fields, and they are members of task groups of SC7. When you wrote your attendance, you could already see the expertise, and afterwards, when we send you the presentation, and that will be present in the presentations as well. So that's why I won't talk about it at this time, because it's good to have a lot of time for their expert presentations instead of talking by me. Well, there are some rules for the webinars. Please mute your mic. You can be able to talk, so the sentence will be left the next time. We have questions through the Q&A, and if you think it's an important question, you can upvote it by the question. We don't have to have time to answer all the questions, but we will do that later on. So all the questions will be saved and the answers will be provided later on afterwards. This webinar will be recorded, so you can look back to the webinar, of course, and the presentations and the Q&A will be linked afterwards and sent to all the attendees and will be present at the websites of ISS MGE and from NEN. Then I guess it's best to start with the webinar and to give the screen to Hakan without further ado. I try to stop. Hakan, the floor is yours.
Thank you very much. My name is Hakan Garin, and hopefully you all can see my presentation on the screen right now. Please verify, Kurt.
Yes, that's right.
Yes. Ground properties. Today's topics. That's Eurocode 7 Part 2. And my name is Hakan Garin. I'm working in the company of Eurocode in Sweden. I am at the moment the convener of SC7 Task Group C2, but I have previously been involved as one of the main authors of the second generation of Eurocode 7 Part 2. Second generation. The European forward says that this has been drafted to be used in conjunction with the relevant execution material, product, and test standards, and to identify requirements for execution material products testing. That's what's in the European forward. And in Eurocode 7 Part 2, it says EN97 established the rules for obtaining information about the ground at the site as needed for design and execution of geotechnical structures, including temporary geotechnical structures. So it's very well established, the relationship between the Eurocode and other standards. and that part 2 actually supports with the rules and the relation to large number of standards. But why do we need geotechnical data? To make it possible to verify structures like this in a harbor, and to describe such a material as the peat, to describe it and use it in our design and our work. As long as we work with this soft material up to very hard material as rock. So, and everything in between. That's geotechnical material, ground material to use. Why? To make it possible to verify ground improvements like this one. This is one example of ground improvements that is covered within Eurocode 7, but we need the properties so we can verify it. We can verify it and we can work within permanent or temporary works, for example, for infrastructure like here, and to verify the conditions for pile foundations, along other things. But part 2 is not only to use with large projects. We have ordinary to verify the foundation for a small project like this one, a single family home. So it covers the whole spectrum from small to big, to complicated to simple, from soft to hard, to facilitate so we can actually work in a safe environment of the execution of foundations. For example, in this excellent situation here, and to facilitate so we actually avoid dangerous situations like this one. Take a look at the slope, the cuttings. Not very safe. That's why we need geotechnical data. This is from this first generation of Eurocode 7. In part 2, this figure is figure 1.1. It shows the path of geotechnical data from field and laboratory testing, F and L, with eventually, if any correlations or transformations, to get the test results and derived values. That's within part 2, and the rest is in part 1 today. The path in the next generation is very similar to this one. In other words, you start always in part number 2. So part 2 is the starting point for the data. So, well, what do we got in part 2 here? From ground to design. Yeah, this is a better way to illustrate it. The figure is the part of a guideline that will be published in early 2024, a guideline for assembling the ground model and derived values. But in part 2, we start with a desk study. We have the site visit and we have the land use and everything around it. We go through the process of finding preliminary design, preliminary investigations, design investigations, and we are still within Eurocode 7 part 2. But we are not into design value, but we are still working with test results and derived values. Because it's when you go into the next step, you are going into Eurocode 7 part 1 and part 3, that's where you find the design value representative and the design values. They are shown and presented in part 1 and part 3. It's all connected. So I'm talking about parameters and properties, and the topic for today is ground properties. But what's the difference between parameters and property? We can easily read in Eurocode 1990, which is already submitted, in 7.3, design assisted by testing. Physical testing may be used to determine parameters for use in design. In Eurocode 0, we talk about parameters. But in Eurocode 7, part 1, the definition is ground property, a physical, mechanical, geometrical, or chemical attribute of a ground material. And in Eurocode 7, part 2, we also talk about measured value of a ground property. Value of a ground property recording during a test, for example. So in Eurocode 7, we talk firstly of ground property, and then a parameter is used when you go into the design. And everything here you can see on the right, we have a small pyramid. On top, it's 1990, and below it's 1997, part 1, 2, and 3. You always have to read 1990 together with 97 to find what you need. We have definitions in 1990 today that has been moved from Eurocode 7. So, what's new? What's the situation? What's the suit of Eurocodes? Here we have the first generation of Eurocode, 1990, 97, part 1, and Eurocode 7, part 2 on top. And the second generation is a little bit larger. As you know, we have 3 parts of Eurocode 7. And if we take a look at what we are dealing with here today, it's the ground investigation and testing. That's the name of Eurocode 7, part 2 for the first generation. It has changed name because it has changed the content. The content is sorted in another way, and that's why the name of Eurocode 7 part 2 will be ground properties, because it's a development. And if we take one step further and see what's the difference between the first and the second generation regarding part 2, you can see that the first generation, the scope for Eurocode 7 part 2 is, Eurocode 7 part 2 is intended to be used in conjunction with Eurocode 7 part 1 and provides rules supplementary to part 1 related to planning and reporting, general requirements, interpretation, evaluation, derivation of values, example for application of field test results to design are given. It's a little bit gray what's actually it's in part 2. But the scope for the second generation is much clearer. This document provides rules for determining ground properties for design and verification of geotechnical structures. This document covers guidance for planning ground investigation, collecting information about ground properties and groundwater condition, and preparation of the ground model. This document covers guidance for the selection of field investigation and laboratory tests to obtain derived values, and fourth, covers guidance on the presentation of the result of ground investigation. With other words, Eurocode 7 part 2 has shifted from a handbook over to useful requirements. At least that's my opinion about it. So, what was the philosophy behind Eurocode 7 part 2? To see the philosophy of part 2, we have to start in part 1. Because part 1 is the one who is guiding you as a reader, as a user, into part 2. The scope of part 1 says in bullet point number 3, This document is intended to be used in conjunction with Eurocode 7 Part 2. FPR is just the preliminary version, but it will be EN 97 Part 2, which gives provisions for determining ground properties from ground investigations. And regarding material, says that ground properties shall be determined according to Eurocode 7 Part 2. But if we go into Eurocode 7 Part 2, it says the provisions and the references are there. As you can see on the right side, there is the pyramid. In Part 2 in Eurocode 7, we have 3 normative standards. They are normative. They shall be followed. That's EN 14688, 14689, about description and classification of soil and rock. And then we have European Standard 22475 about sampling of soil, rock, and groundwater. These 3 standards are referred to as normative in Eurocode 7 Part 2. Then we have a large number of highly recommended standards. They are 43 European and ISO standards related to material testing, etc., which actually forms the basis for Eurocode 7 Part 1, 2, and 3. These 43 EN and ISO standards, together with the 3 normative EN standards, forms the basis for the pyramid, Eurocode 7 Part 1, 2, and 3. Then, together with this shall, should, we also have some permissions in Eurocode 7 Part 2. These permissions are ASTM, ISRM. These documents are permission to use, and then we have some national standards, because not all test methods, for example, are covered by European or international standards today. They are available as national standards only at the moment. British standard, Swedish standard, etc., etc. If they are not available as an EN standard or an ISO, they may be used. It's a permission to use them. So what's the content of Eurocode 7 Part 2? The content is here. Here's the table of content. Quite comprehensive, but I will try to guide you through. Start with the introduction, scope, normative reference, and terms and definitions. These 4 sections are the introduction and the definitions. This is the formality. These are good to read, well needed. You need to read section 3. It's very important to have the basis covered. Then we have 2 sections, section 4 and 5, which are the ground model and derived values, and the ground investigation. The process of getting information from field and laboratory up to derived values, including the ground model and the ground investigation report, are described and introduced here in section 4 and 5, together with section 13 about reporting. Then we have a package of section 6 until 12, where we have from the beginning description and classification, 7 state physical and chemical properties, 8 strength, 9 stiffness and compressibility and consolidation. Then we have 10 cyclic dynamic and seismic properties, 11 groundwater and geohydraulic properties. These 6 sections were present in the first generation, but then we have section 12, chapter 12, thermal properties of the ground. That's a new one, because it's opening up for tomorrow, where we actually need to use the ground in a much bigger way as a source for thermal part of human beings. We need it. So it's opening up for the verification and design for tomorrow. And then we have 13 about reporting. Together with this, this covers about 2/3 of the number of pages. 1/3 of the number of pages are all the annexes, Annex A up to Annex H. These annexes are related to different parts of the main text. And they should be read together with them. And they are informative annexes, but highly recommended, but still an informative annex. And after my presentation, Sebastian Futti will talk about these 3 sections. Marcus Arroyo will talk about section 8, strength. And Christian van der Made will talk about an example of the total in the whole. So, why is Eurocode 7 Part 2 essential? Eurocode 7 Part 2 in the first generation, not all countries accepted or implemented that part. Eurocode 7 Part 1, yes, but Part 2, no. But the second generation, Part 2, will definitely be implemented around Europe because quality, and I put my neck out here, I say you cannot compensate for bad input by using a partial factor. You need to have quality from the beginning. So what we have here in Eurocode 7 is Part 2 is quality classes, table 5.4 and 5.5. My partners will talk about it later, so I do not go into details. Quality is also how we determine the ground properties, because ground properties, according to Eurocode 7 Part 2, can be determined direct, indirect, indicative value, and table value. And what's that? 4 different ways. Yeah, it's also an indication of the quality of the information, because take, for example, density. If we have direct measurement, we measure the mass and we measure the volume. That's a direct determination of the density. An indirect determination is maybe a function of the water content, but then you need to assume, for example, the density of the material, the dry density, etc., minerals. But it's a function of the water content. That's an indirect method to determine the density. Indicative. I don't know if we have good rules for indicative determination of density, but we have table values that we go see, okay, in this area, other users has experienced, oh, the clay has a density between 15.5 and 16 kilonewton per cubic meter. For example, that's one way to actually see. It's top quality at the top and it's less quality in the bottom. So you need to work with the information as you get, as good as possible. Quality is also another thing. Quality is a property. The property is a set of information. Because if you only have, let's say, the density, the value of itself is not a quality information if you don't know anything about the uncertainty. If you know that the density is, for example, 16 plus minus 0.5, or if it's 16 plus minus 1.5 kilonewton per cubic meter, it's a very large difference. So you need to know, you need to have knowledge about the uncertainty. Otherwise, the value itself is of no use. No use is maybe too much, but it's not that high value of that information. So in Eurocode 7 Part 2, we have this simplified overview, okay? A lot of people say that's not simplified, it's quite complex. Yeah, but this schematic outline also have in the bottom what you can read here in yellow: low confidence, medium confidence, and high confidence. The confidence levels are a little bit a red thread throughout Eurocode 7 Part 2. Because if you have a high confidence level, you can rely on the information in very good, very high level. If you have low confidence, you have to be careful. And then it's a scale. So in this diagram, this table on the right, you see numbers 1, 2, and 3, and these are related to low, medium, or high confidence applicability. So if we look at quality another way, this is the information here. But we also need quality by qualifications and competencies. Eurocode 7 Part 1 in the scope assume in bullet number 1, in addition to the assumptions given in Part 0, Eurocode 7 Part 1, Eurocode 7 assume that the ground investigations are planned by individuals or organizations with knowledge of potential ground and groundwater conditions, executed with appropriate skills, geotechnical experience and qualifications, experienced individuals, verified by appropriate qualifications and experience, and the data collection and the communication in design, verification, execution. That's a lot of assumption, but that's needed because we have requirements for Part 1, 2, and 3 that if you study this, let's say, first bullet point, yes, it's definitely related to Eurocode 7 Part 2. This one, to Part 2. This one, definitely to Part 2. This one, both Part 2 and Part 3, and of course Part 1. Verification and design, that's Eurocode 7 Part 3 and Part 1, yes. And the last bullet says adequate continuity communication. That's between all, but it also involves Part 2. So you have to realize that if you want to have quality, you have to start with quality from the very first beginning, because you can't save the design by a partial factor if you have bad input. And by that, I say thank you very much. And I now open up for any questions. Please, Gert.
Yes, Hakan. There was at this moment, apart from a few questions from will the presentation will be sent afterwards.
You are muted.
You can hear me now? You can hear me now? There was only one question. Will reporting include any guidelines on the presentation, on the preparation and need for geotechnical baseline reports? Syria published in January 23 a guideline to these and to use the needs for clients to prepare these. Does SEN and the Eurocodes have anything on this? Then Marcos answered for you, yes, look at part 1, chapter 10.4. So these were all the questions for now. So you have a very good story, Hakan. It's very clear, I guess. And we will give the word to Sebastiano. Idi, gaat goed?
Yes.
Sorry.
Okay.
Yes. Thank you, Gert, and good afternoon, everybody. Firstly, I introduce myself. I am Sebastiano Foti. I'm a professor in geotechnical engineering at Politecnico di Torino in Italy. I'm a member of the Italian Geotechnical Society, and I've been, as Hakan, part of the team who drafted drafted the part 2 of Eurocode 7 we are presenting today. Specifically, as I can remember, I'm going to talk about 3 different sections of part 2, that is clause 7, that is devoted to state, physical, and chemical properties. Then clause 9, stiffness, compressibility, and consolidation, and the associated annex, that are the methods for determining stiffness and consolidation properties. And finally, clause 10, cyclic dynamic and seismic properties, and the associated annex G. Specifically, clause 10 is something that is new with respect to the previous version of Eurocode 7. Indeed, it has been drafted in order to make a connection between Eurocode 7 and Eurocode 8, specifically with Eurocode 8 Part 5, that is dealing with the seismic aspect in geotechnical engineering, and that basically required some specific input from the point of view of ground investigation. So it was decided to add specifically this clause, and it has been drafted in this view, in this perception, but not only with reference to seismic properties, but to all geotechnical
Can you share your
problems.
presentation, please, Sebastiano?
Okay, I thought it was. Sorry. Okay, now it should be okay. And so I was saying that clause 10 was specifically added also as a connection with the Eurocode 8 Part 5, and it deals, but more in general, with all the parameters that we need for cyclic and dynamic problems in geotechnical engineering. A note about the presentation: whenever you are going to see a green box or a text that is in green, these are personal material, so it's not part of the Eurocode, but has been added by myself in order to be more clear in some of the aspects that I'm going to deal with. So let's start with clause 7, that we can say deals with the basic properties of soils. As Hakan was saying, the new organization of Eurocode 7 Part 2 is basically driven by parameters, by properties and parameters of the ground, and is taught to provide the tools, provide guidance on population of a ground model with the parameters that we need for design. So clause 7 deals with the basic properties of soils, starting with state properties, and here you can see the general table of contents of clause 7.1, state properties, that deals with bulk mass density, water content, porosity, saturation, density index, and in situ stress state. Starting with state properties, there is a list and a table that describe field and laboratory tests that we can use for determining state properties. One important aspect that I think it is to be stressed is always the association between the properties that we want to derive, the type of methods we are using, either direct or indirect method, and specifically the quality class of the sample that we need to use for each determination. So for example, you see over here for the bulk mass density, quality class 2, or for the water content to quality class 3. This is referred to the table that Hakan was showing before. So the table that describes the use that we can make of a sample depending on the sample category. So depending on the technique that we use to get the sample and to take the sample to our lab. So I think this attention has been done through the whole Eurocode 7 part 2 to point out the importance of good quality of the samples. The other important aspect that we will find through all the different aspects, different parameters, is the reference to test standards, so that for each one of the tests that is considered, we can have a direct reference to the appropriate standard to be used. First parameter in situ stress state. Here we have the test that we can use either directly on site or from laboratory test in order to evaluate the in situ stress state, and some notes about the applicability of each one of these tests that is guidance for us. Also an important something that is the possibility that we can use simplified approaches, like for example the well-known formula to get a keynote value that describe the coefficient of earth pressure at rest, that is coming from the literature, is well known and accepted approach, and it is important to notice that whenever we have a MA, so we have a permission to use a formula, this means that this is not suggested, but is something that is considered acceptable. And indeed, using a general values, this one coming from a general formula, not from specific test, may be accepted in some cases. These are stated by the code, but is always something that is not suggested, and neither is can be considered as required. Clause 7.2, physical properties. Again, the list of the physical properties that are considered in the code, and again the indication that they should be determined according to the standards, and also the fact that we have to determine for each portion of the specimen that represents different soil or rock type within the same sample. So the importance of having an high resolution in evaluating the physical properties. I will not go through for all the different tests that we can use also in this case, ranging from the determination of particle size distribution, active Berlin, particle density. These are quite standard approaches in geotechnical engineering, but obviously it is a matter of having the full range of possibilities that are outlined and commented in part 2 of the code. Compatibility, clause 7.2.9, again the test that we can use and the quality that are required with respect to the standards. And here we also have indication about man-made material, so the possibility of using proctor and modified proctor and vibration test to define the optimal water content. This is dealing with construction material, and again, it is important to observe that it is a permission whenever we say may. Clause 7.3, chemical properties. Chemical properties sometimes are understated in our projects, but it is always very important to understand the possible interaction that we have and the possible consequences of construction of our work. So from this point of view, here you can find again the list of the chemical properties to be determined and the laboratory test that we can use for the determination of each one of these. A note about chemical properties is that we can use disturbed sample, and here it is. They identified this aspect, saying that we can use quality classes from 1 to 1, up to the point in which they are representative of the soil in situ conditions. The other aspect, obviously, in soils that are porous media, in which the voids are filled with water, is that the chemistry of the water has a large influence on a specific problem that we can have with soils, and so it is suggested, strongly suggested, again, this is a should, that the chemical characterization of water as a minimum should include the identification of carbonate and carbon dioxide content, sulfate content, pH values, and magnesium content. These are considered as minimum standard for the characterization of the water in Eurocode 7 part B. Shifting to clause 9, dealing with stiffness, compressibility, and consolidation. Let's start with stiffness. The suggestion, again, this is a should, is to describe the ground stiffness in terms of the full stress-strain curve over the expected stress and strain range for the anticipated design situation. And this is also something that we find consistently throughout Eurocode 7. The reference to the design situation means that whenever we are dealing with our parameters, we are identifying our properties, we always need to have in mind what we are going to construct. So which is our final objective of the design, and explore the behavior of the soil, having in mind the design situation that can be anticipated, that we have in our mind. As a permission, ground stiffness can be approximated with one or more values of elastic moduli. And when we are talking of elastic moduli, obviously we have in mind that linear elasticity is not a model that fully describes the behavior of soils, but is a good approximation if we consider a given range of strain that applies for, again, the design situation that we have in mind. From this point of view, an important the guidance is provided in CEF, where indeed it is reported the level of strain that we expect for the typical geotechnical problems that we can encounter. And if we describe the variation of the stiffness of the material in terms of a second elastic modulus against the shear strain, then we can divide the behavior of the material in different portions, considering the very small strain, in which basically a linear elastic approximation can be considered adequate, and we have a small strain shear modulus that is almost constant, and then ranging to small, medium, and large strain. And our geotechnical problems typically fall in different levels of strains that are identified in this graph that is reported in Annex F. And this can provide a guidance to understand which is the relevant value for our problem, and then in conjunction can lead us can guide us in the choice of the appropriate testing technique. Indeed, ground stiffness should be determined directly from test results, and again, this is something that is consistent through part 2. The suggestion to use, whenever possible, direct determination from test results, either lab in situ tests, but that can provide us a direct determination. From this point of view, it is the factors that shall be considered when determining stiffness are outlined in and especially we have to pose our attention to the importance of in situ stress state and the stress history of the material that needs to be taken into account. And other aspect to be stressed about ground stiffness is, as I said before, the behavior at very small strain that can be explored using methods based on the propagation of shear waves or other dynamic methods, either directly on site or on samples in the lab, and the fact that the stiffness decay curve that describes the change in stiffness with strain can be determined using a range of tests. They are reported for the direct determination in table 9.1, and they range, again, as said before, from in situ test, specifically geophysical test for the very small strain shear modulus, so for the very at the very beginning of our stiffness decay curve, so in this zone, to other possible tests on site that I here described that provide possibility of exploring the stiffness at different strain levels. So they are reported again in this graph that comes from Annex F. With respect to geophysical tests, so the small strain shear modulus, it is also possible to make reference to table 10.2. We will be back on this later on. On the other side, we have laboratory testing. Again, it is stressed the importance of working at the strain level that is expected for the specific design situation, and here a list of properties in terms of stiffness and how can we define them in laboratory testing. A note about quality class of the samples. If we are dealing with stiffness, we always need to use high quality samples. This is particularly true for stiffness. And also another note that is related to the fact that especially when we are dealing with small strain models, it is specifically important to have to ensure the quality of the sample, and we need to use techniques for getting truly excellent sample to the lab. The alternative for the small strain model, as we said before, is to go on site with geophysical testing. Back to the topic of the quality of the specimen that we use in the lab, we have indication in Annex F again, specifically in Annex F point 3, where details on quality of the specimen are reported, ranging from a qualitative assessment by visual inspection, that is obviously the first basic step that we can use in the lab, to a more quantitative assessment that can be based on the behavior of the specimen in terms of the volume change at the estimated in situ stress state. This is something quite well consolidated in the literature. If we have a reduced volume change when we get our sample to the state of stress that it had on site, we can think that our samples are our specimen are very good to excellent. So this table is a guidance to describe the actual quantitatively, the actual quality of the specimen that we are using. And if we look at this graph from the literature, we see that the change in volume is a possible parameter. The other parameter that describe quite well the quality of the specimen is the ratio between the measurement of the shear wave velocity in the lab against the measurement in the field. So in the material as it is in its natural state. And again, this can be used as a proxy for the quality of the specimen.
Sebastiano,
Yes.
you have only a few minutes left. I don't know. I saw
Okay.
more sheets, so this is for your information. You have a few minutes left for your presentation.
Okay, about the indirect determination, again, we can find some specific indication in table 9.3 and indication from the back analysis. Ground compressibility and consolidation, about load compression curves and the compression parameters that we that describe the behavior of the soil in terms of compressibility. They can be determined again directly from lab and in situ test or indirectly with empirical correlation. So we'll switch to clause 10 about cyclic and dynamic properties. As I said before, this has been included also as a conjunction with the Eurocode 8, so specifically part 5. And it reports the aspect that we should consider when selecting a method for testing the soil for its cyclic and dynamic properties. About laboratory tests, similarly to what we have seen for stiffness, the importance of using samples of quality 1 and a guidance on the use of different possible techniques depending on the range of strains that we have to take, that we needed to take in consideration, considering the expected design situation. And a note about the possibility of using reconstituted specimen and which are the conditions in which we can use reconstituted samples. About the behavior of the material in cyclic condition can be described in terms of stiffness decay and damping ratio curve, and these can be obtained directly from the test that we have seen before. They can be determined indirectly with empirical relationship. In Annex G, we find some possible relationship to be used. For example, you see the corresponding graph over here. And in terms of the evaluation of the very small strain moduli, we use typically geophysical test in the lab, and here you see, as I announced before, the test describing all different geophysical tests. And in this respect, it is important to notice that actually at the present time we have no European standards for most of the tests, and for this reason it is important to make reference to other possible standards. I reported over here a few indication of international standard can be used, and also guidelines specifically here for surface wave testing that are often used because of their cost compatibility, and they you can find more details over here. The shear wave velocity and very small strain moduli can be also determined indirectly, and also here we have a correlation that are reported in Annex G, for example, for the most common test like cone penetration testing and standard penetration testing. And going on, we have the part related to excess pore water pressure evaluation that should be investigated in the lab, but again, we have the possibility to make use of indirect estimation with empirical correlation. Here you have an example of a possible empirical correlation. Same for cyclic Andrade shear strength that has to be defined with respect to the effect of a given number of cycles in terms of available shear strength. This should be investigated in the lab, but more often, especially for coarse soils, this is not easy to get undisturbed sample to the lab. So it is stated the possibility of using empirical correlation. And for this, a direct reference to Eurocode 8 part 5 is included in the code. And for fine salts, it is important to observe the possible effect in terms of degradation and the effect of the possible effect in terms of strain rate and the potential increase that we can have in cyclic undrained shear strength because of the strain rate effect. If both of them compensate each other, we can directly use the values that we get from monotonic test. This is stated in the code. Finally, this is really the last indication about cyclic and dynamic properties. One important aspect for seismic characterization is the evaluation of the position of the seismic bedrock. In this respect, it is stated that we should make use of geophysical method that allow us to evaluate the shear wave velocity to identify the seismic bedrock. In alternative, we can also use compressional wave velocity whenever we have a good contrast in terms of stiffness between a soil deposit and the underlying bedrock. And in terms of the fundamental frequency of the soil deposit, it is an important parameter for seismic site response. There is an opening to the possible use of the single station horizontal to vertical spectral ratio survey that is often used for a direct determination of the fundamental frequency. Here you have guidelines that can be used in this respect. And with some final remarks and to close, I think that the final remarks are in line to what Hakan stated before, especially about direct and indirect determination. Direct determination of parameters is always to be referred, but it requires a specific expertise. And on this, Hakan has spent a few words. So it is important that both the equipment and the people are skilled for the test, but in general, direct determination is to be preferred. Indeed, you can notice that in most clauses, direct determination is associated to a should condition. Indirect determination is based on empirical correlation, so therefore we typically have large uncertainty. Indeed, we have experimental uncertainty, and plus we have also implicitly the uncertainty that are included in the transformation. So in the code, you will see that indirect determination is always a may. It is possible, but it's not suggested. And finally, we have still a lack of standards, especially for the cyclic dynamic and seismic properties, and I hope that this could be filled soon at the European level. So thank you very much for your attention.
Thank you, Sebastiano. Looking at the time, we will take on questions maybe later on, and I will give the word to, if you close your presentation, I will give the word to Marcos.
Okay, hello. Let's see. Okay. And now. Ooh. Can you see the starting page of my presentation?
Yes, but I cannot see if it's in correct presentation mode.
Oh, you cannot see my face. This is what you're complaining about.
No. Check the next page, next sheet. If it's working, it's okay.
Is it okay?
Yes.
Good, excellent. Thank you. So, thank you everyone for attending this chart with introducing some concepts as presented in the second generation of Eurocode relating to strength and strength parameters. And this is the outline of how of the points I will be making, which some of them you have heard already, but probably they are worth repeating. You might wonder why Professor Foti was charged with 4 chapters and I'm just free with discuss a single one. And that I think that probably the reason is that strength properties, well, it's not that they are more important, but they, for instance, they appear in part 1 because they feed into some ultimate limit state verifications, and they appear associated with partial factors. So, of course, as you will see, chapter 8 in the future and the second generation Eurocode 7 covers more than just those properties that are a factor in part 1. But I think that is interesting to start by this. And this is not the second generation. This is first generation. And I'm just bringing here this so you can check immediately what has changed. See, we have 1, 2, 3, actually 4 properties related to strength. When we move to this second generation, the equivalent table, which is in, I repeat, in part 1, is bigger. It's bigger. If you go counting all the lines, you will find that there are, I think, 13, so 3 times more. Why is that? Well, I mean, you have here, I have synthesized what I see as the main novelties. The first important, very important novelty is that the previous generation didn't bother with rock, with everything. The Eurocode had been written to do geotechnics only in soils, and now it encompasses all kinds of ground. So rock has been included, and there are some specific properties associated with rock and its determination, and of course some different partial factors. You see that there is also a distinction between rock material and rock mass and rock discontinuities. There is also a novelty, which is interface strength. Interface strength is relevant because now the Eurocode will cover as well reinforced soils, for instance, with geosynthetics, and that is a highly relevant property, not only for that, but I suppose that the fact that now is there at the forefront is partly related with that broader scope of this second generation. Then, when you look just at soil, you will see also more than 4 properties here. And the reason is that there are several reasons. First, this first line, which is very abstract, shear strength in effective stress analysis, if you were to read the note, that is related to numerical analysis, in which sometimes you won't actually factor the parameters, but you will look at how mobilized shear strength can be reduced. And there's also here several, for instance, friction angles, peak, critical state, residual. There is a distinction that has appeared now. And then finally, there is something related with the undrained shear strength. The terminology has changed. Let's have a closer look at these 2 last changes. This is related with those distinctions about some of the strength parameters, not just for soils, also sometimes for discontinuities they are relevant. But this idea that in many circumstances the shear strength of a relevant material will depend on the level of straining. It might go through a peak and then approach a critical state. For instance, a critical state, a state in which the soil deforms at constant stress and void ratio or volume. that is a relevant distinction. You should be aware, and the code puts that at the forefront. You should be aware of which kind of strength are you dealing with. And also in some circumstances, as you keep on shearing, for instance, this is a classical graph from Skempton related to slope stability, and in which he was making the point that for plastic soils with a high clay fraction, if you kept on shearing a lot, you will attain even lower levels of shear strength. That will be the residual shear strength in the case of soil. So that is a distinction that is now there at the forefront. And before talking about the terminology issues with undrained shear strength, let me just share with you a reflection on what all this Eurocode drafting has been for me. I mean, sometimes, well, it has been an experience of collective action. And collective action sometimes has these results on beautiful outputs, like, for instance, this Castell, which was a record. And, you know, this is a kind of sport that is practiced in the region I'm living in, Catalonia. And so this is the nice side of collective action. But there is also this other side, the side in which, well, you're trying to cook a broth, and perhaps the cooks all try to do their best and give their best recipe, but sometimes the output, well, doesn't taste like anything anybody had imagined. So, and that is my view, has happened a bit with the undrained shear strength, the terminology that is used now in part 2, because even if we have this very clear definition included in the code, and it's very transparent, and is what you will imagine that it will say, well, despite this being there in the definitions, throughout the code, you will find this kind of terminology, sometimes undrained shear strength, but sometimes shear strength in total strength analysis, which is a bit of a mouthful, and sometimes cohesion in total stress analysis, which I think is not quite right. So, I mean, just for not to discuss that anymore, I will indicate with this wooden spoon sometimes when I think the code is actually talking about undrained shear strength. Let's now move to something that is also there at the forefront. If you go to chapter 8, part 2, the first section is devoted to what the code calls strength envelopes. What are strength envelopes? This is a definition is given. It's an envelope. It's an expression that defines the boundary to failure in the material under shearing in a stress space. Shear strength envelope. Actually, you might wonder, well, what happens with a tensile failure? I mean, for instance, for reinforced ground or for, say, jet grouting, something like that. Well, actually, even if that's the definition that is given, then in the code text, it is more general. It's giving you permission to describe ground strength in terms of total or effective stress using strength envelopes. And there's no mention of shear here, so that can be applied in a more general way. Another thing that appears in this slide is that I will use this kind of color code to convey to you where the code is giving permission, that is with this sky blue or pretend sky blue, and when it's being more strict, when it's actually ordering you to do something. Those are the shalls. And then there will be also some occasion for recommendations that those will have other color. But you see, that's interesting in the sense that in part 2, many aspects, there is a lot of leeway in principle. You have freedom to choose or not the strength envelopes to describe the strength of the ground that you're characterizing. But then if you actually use strength envelopes, then well, the you have to be precise. You have, for instance, to express what is the applicable stress and strain range, or the strength condition. Is it peak? It appears for peak, for critical state, for residual conditions. No? So, and that we'll see happens again and again. In that section, the code is going to propose, you see, is going to propose a number of classical strength envelopes that, well, they are put forward as possibilities. And you see, the first one obviously is more Coulomb, which is very often used in many models. And there are a couple of interesting caveats here. One is that the code in this note says that you cannot go on, and if you're going to use a more Coulomb envelope, you have to simultaneously determine friction and cohesion. You cannot just say, first I will do friction and then I will adjust cohesion. And also there is this interesting bit, which is enforced about if you're going to use critical state conditions, then there is no cohesion there. No? In total stress, there is what I think is a complicated definition, but this thing here is essentially undrained shear strength. So this is my spoon to remind you of what it is really talking about. This, the next envelope that is introduced in the code is one of them, an important novelty in my opinion. In the first generation, there was no consideration at all, or really very little, of unsaturated soils, of soils that are in an unsaturated condition. Now, the code proposes what is a classical strength envelope for unsaturated condition. There is a typo here because that should be the pore air pressure. I think that will be corrected. But essentially, what we're looking at here is a more Coulomb envelope in which you see the cohesion intercept increases with suction or as the degree of saturation decreases. No, so it is interesting that if you go then to part 1, there is this shall here, this condition, which says that suction, and therefore this kind of approach shall only be considered when the anticipated degree of saturation will be maintained throughout the design situation. So I presume that that opens a world of possibilities, at least for transient conditions in dry countries, at least like mine. I don't know, maybe not in very northern countries, but in dry countries that will be interesting. Then strength envelopes are proposed for rock material and rock mass. The one that is suggested is a nonlinear envelope, the Hawk and Brown strength envelope. I suppose that is familiar to most of you. It is here described, and some of the notes describe how some of these parameters are evaluated in some cases. This nonlinear envelope can be linearized, and you can also use linear more Coulomb envelopes to describe the strength of rock material and rock mass. For discontinuities, in which there is rock-to-rock surface contact, there is also the possibility of use a nonlinear strength envelope, the Barton bandis, that depends in measures of roughness of the walls, of strength of the walls, etc. But there is the more Coulomb linear envelope is also apparent here. It is interesting that in this case, you see, there is this simpler one, but in the notes they're telling you that as often happens in the techniques, if you choose the simpler model, you need to be careful because it will apply to a more restricted set of conditions, and particularly you need to be careful if you're extrapolating to low normal stress. And this section of chapter 8 ends by opening up the field, saying, well, those are some basic proposals, but you can come with something else. And interestingly, that what is saying, well, it's open here, and then here again you see open at the beginning, then restrictive. But if you're going to use something different, note that they are considered as calculation models and should be validated accordingly. And also that you should show how this implicit, for instance, something that is in a numerical model, you shall show how it behaves under simple stress conditions like triaxial compression, triaxial extension, simple shear, something like that. But this term here, what does this mean, validated calculation model? Maybe you have heard that if you have already followed all these seminar series. But even if you have heard that, I think it's worth making this point again. This is a table in part 1. And it's a table, by the way, that all of you will be adapting in the near future, because it's a national determined parameter that will take probably different forms in different countries. But essentially, the shape won't change. And that means that depending on the geotechnical category of the structure that you will be designing, you will be required to validate a model, for instance, in this case, a strength envelope, but that applies more generally, with a number of measures like documentation, verification, etc., etc. Anyway, that is enough about strength envelopes. I will move now a bit to what chapter 8 says about soil strength, and that will allow me to insist on this issue of direct versus indirect determination of properties. You see, for instance, direct determination of soil strength properties. You will find there a table in which there is it is organized around properties. And you see, for instance, peak, effective cohesion, and friction angle. And you say you have all these 4 possibilities to determine that directly. By the way, direct determination is recommended. You see, those things should be done. It's recommended. It's not compulsory, but it's recommended. And you see that most of these ways of directly determining relevant strength parameters are by means of laboratory tests. Of course, laboratory tests are associated to a sample, and that sample has to have some quality. So here are requirements on the quality of the sample as they were discussed for stiffness before. You see, there is one here for the peak, and here there is a range, because when you go to see these notes, they tell you that in some soils you can actually reconstitute. And reconstituting the material, well, it doesn't require high quality samples. I mean, you can, but you need to know, as the code tells you as well, what is the target density, for instance, for reconstitution. So most of them are lab tests, but some field tests are also deemed, for instance, the field vein, that are also within their field of application, as explained in notes in the code. They are able to produce directly some soil strength properties. There is also, as it was discussed before, reference to the procedural standard for the test. And here the code, as you have been told, but I repeat, has a preference for European or ISO standards. And but sometimes there is no European or ISO standard for doing something. So in that case, well, it is recognized here. And if you, but not to leave you hanging without any idea about what to do, the code has included in an annex, in an annex that is informative, a number of possibilities of national or different standards that are not European for the and that can be used until an European standard comes to eventually replace them. So you will find things like ASTM or others that I will mention in a minute. So this is about direct determination of strength properties. For instance, you do a triaxial test, you do a direct simple shear, you do something like that. But of course, there is then the possibility of using indirect determination procedures. Again, here what is the kind of tests that are relevant for indirect determination are mostly field tests, but you see there are also some lab tests. I mean, you can use, for instance, the fall cone, which is a lab test, or you can use the consistency limits to estimate something. No? And what is indirect measurement? That is not defined in the code, but this is the idea. We measure something else and infer the property of interest through a transformation model or correlation. I have taken that from one of the forthcoming guides that have been designed to help interpret some aspects of the second generation Eurocode. This one deals with many more things, reliability, background of the Eurocodes, like everything vaguely probabilistic is addressed in that forthcoming guide. And for instance, it has very useful definitions of what is a transformation model. Uses a property measured in situ or at laboratory to predict the design ground property. And sometimes we just call it empirical correlation if we're not up to date in the mores of academia. But here you see, I mean, this graph I find particularly useful because it conveys this idea that when we're doing this kind of exercise, we will always carry some error. All these dots will never fit into the line. Ideally, your transformation model will fit right in the middle. Sometimes, for reasons we cannot enter into them, it will be biased. But if you know that it's biased and you can correct for it, there is no major problem. Now,
okay, Marcos,
yeah.
you have a few minutes left.
Excellent, excellent.
Okay.
I don't need anything more, because this is again, you see, there is this freedom, this possibility to use transformation models, but then if you use them, then the code becomes strict. You have to comply with 4.2, and in 4.2 it says that if you're using an empirical correlation, first you need to tell us if it is providing average, superior, or inferior values, and then we recommend that you specify what is the materials to which your correlation apply, what is the database that supports the correlation, what are the estimated transformation errors. And also, it recommends that you use site-specific data to support generic correlations. Let me just convey these conditions with an example, because in the annexes, there are some examples of correlations that have been framed in a way that sort of comply with those recommendations, those generic recommendations. For instance, there is one particular correlation in which the angle of peak effective friction for granular materials is obtained from SPT. And it gives you this formula, the minimum of this expression and 45, and this is the meaning, and then this is important. This formula should only be used. And then here are the things that you always have to specify if you use this or other correlations. The kind of soil to which it applies, those are limitations. What is the standard error of the formula, and where is the original database that supported that formula? Well, I'm finishing now, Gert, just with a couple of things about rock strength. Just saying that there are tables in which there are also references to lab or field tests. Here we don't have ISO standards, so ISRM procedures are referenced systematically in Annex B5. When you consider rock mass strength, this is another novelty. Reference to classification schemes are also included. This graph particularly is not included in the code, but this reference is pointed out as one possibility. I mean, the geotechnical, the geological strength index is reference to. So that is all for me. Thank you very much for your attention.
Thank you, Marcus, for your explanation and your presentation. Well, in my opinion, it's important that you all send out your presentations with all the information. Therefore, I sometimes let the time a bit go in spite of the questions later on. We will answer them on paper afterwards. So I will give the word to Kees-Jan. We see your screen, Kees-Jan, but not the full presentation mode. I hear you are working on it, so that's good. We can't hear you, Kees-Jan.
Yeah, it doesn't seem to want to
Okay.
be able to share my screen.
Okay.
Let's try again.
Marcus, did you close your presentation? I guess so. Yes.
Okay, can you see my screen now?
Yes, yeah, we see your screen in the left onderin, Jan, of Kees-Jan. Daar moet je even aanklikken bij die presentatie, dat die in vol scherm staat. Helemaal onderin, ergens, bij PowerPoint. Ja.
Ja, all right, there it goes.
En nou nog weer dat bovenste stukje wat Hakan had verteld de vorige keer. Was een van de twee, ik weet niet welke. Yes, okay, it's okay.
Yeah.
Yes.
Okay, good afternoon all. My name is Kees-Jan van der Made. I've been part of several teams working on Eurocode 7. I'm working for an engineering company, and I thought it would be nice to work through a couple of examples. So let's move the screen thing up. Yeah. So I'll start with a brief introduction referring to parts of Eurocode Part 2 as shown by Hakan Garin. Then I'll have to tell you something about the geology of the Netherlands in a nutshell. Otherwise, you will not probably understand where these projects fit into different kind of sediments. And this I will do before presenting the two examples for ground models using correlations and actually following EC7 Part 2. Let's look again at the scope of Part 2, mentioned in the first presentation of Hakan. Part 2 should provide rules for determining ground properties for design and verification. It should provide guidance for ground investigations, for ground properties and groundwater conditions, and the preparation of the ground model. It should provide guidance for selecting field and laboratory test methods to obtain derived values of ground properties. And it provides guidance on presenting these results of ground investigations in the ground investigation reports. The derived values for geotechnical units come from data and correlations gathered during desk study, site inspection, site investigations, and monitoring of ground and structures. And there Hakens showed this interesting figure explaining how all these different parts actually fit together, from part 2 and even the relationship with part 3. The ground investigation should collect all information to define the geotechnical units that influence the anticipated design situations. The aim of the ground investigation shall be defined before the start, and the results should be presented together with limitations, discrepancies, uncertainties, or gaps in the data, as well as deviations made from standard investigation procedures. The ground model shall comprise the geological, hydrogeological, and geotechnical conditions at the site based on the ground investigation results. Variability and uncertainty of geological, hydrogeological, and geotechnical conditions properties shall be included in the ground model. I marked this a bit blue because this is not very simple. I'll come back to this later. The detail and the extent of the ground model shall be consistent with the geotechnical category and the zone of influence of the structure. This is quite something. So the examples that I want to show you, in those examples, we try to follow the code and see what it actually brings. Because some of the bits are quite new and there are some things that we're still working on. So this is the last slide before presenting these two examples. Something about the soil conditions in the Netherlands. In the Netherlands, we have no rock, hardly. And so the first 50 meters of the Netherlands consist of Holocene tidal and fluviatile deposits consisting of clay, silt, sand, peat, followed by Pleistocene glacial deposits and fluviatile sandy sediments. And the Netherlands is in a sinking basin, and we're still sinking. The phreatic groundwater table is usually within 1 meter of the surface, and in the polder areas, which comprise about 20% of the country, the groundwater table in the sandy Pleistocene deposits can be over 1 meter above surface level. For us, in the Netherlands, the main geotechnical risks are associated with settlement and macrostability. Most of our buildings are on piles. So let's have a look at the examples we worked through based on part 2 of Eurocode. The first is quite simple. It's the construction of a family home, geotechnical category 1. It's a freestanding house on a pile foundation without a basement. No buildings or vulnerable infrastructures present in the immediate surroundings. No excavation is required. So the zone of influence, first estimated, is limited to the property boundaries. At the background, you can see where the site is going to be located. That's top right, you can see what it looks like now. So from the Middle Ages until the 20th century, peat extraction occurred through much of the Netherlands. At this site, it resulted in a relatively deep polder area. Ground level at the site was approximately 1.3 meter minus sea level in 2004. In 2005, large-scale earthworks took place and the area was flooded in order to create a lake with artificial islands for housing development. It's on one of these islands that this test case is located. During the desk study, we had a look at which data is available, either national databases or our own databases. So we ended up with a number of CPTs, manual boreholes, and some historic boreholes dating almost back to 1930. Based on the desk study, a 2D ground model was produced in the vicinity of the project. If you look towards the left bottom of the figure, you can see an inset. You can see the points that we took for this profile, 2D profile, and you can see the red position and the red square, that's the house that's going to be built. So we have artificial material at the top. Then we have the start of the Pleistocene sediments, which is BX. That's clay and very fine, usually wind-blown sands. Then we have fluviatile deposits, PE, sands, and we have PE and I. And that's over-consolidated clay. We can do all these correlations based on CPTs. In the Netherlands, we have a lot of experience with CPTs. So for this one, we use the standard correlation to actually make this 2D ground model. But for building a house, this might be a little bit problematic. For a pile foundation, both the sand and the over-consolidated clay of the Pilo formation, that's the PE, in the drawing before, would probably provide sufficient bearing capacity. However, the high lateral variability might result in pile tips lying both in clay and in sand, thus resulting in a variable settlement behavior. The chosen lateral zone of influence appears to be appropriate. And based on the available CPTs, the vertical zone of influence is set at 25 meters. So we started with the first zone of influence before the desk study. And after the desk study, we can set the vertical zone of influence, and which is set at 25 meters. Based on the desk study, a site investigation plan was drawn up. This resulted in 4 CPTs to approximately 20 meters and a borehole with undisturbed sampling to approximately 3 meters. This led to a new 2D ground model. You can see at the inset on the left-hand bottom corner that there were 4 CPTs at the corners of this single house. And you can see that AA, compared to the previous 2D model, the artificial material that was used to hide the site has increased. It's now up to 3 meters. The fine silt and from clay and sand layer is approximately the same depth. And we can see there's a little bit more over-consolidated clay than we expected. And this over-consolidated clay is deposited in steep valleys. So if I look at this drawing and the distance between CPT 6 and 7 and 8 and 9, then there's a lot of uncertainty regarding where these pile tips will actually end up, because they're usually quite steep. So 3 more CPTs were suggested based on this phase 1 to allow for less conservative pile calculation. So this is the model we actually ended up with. based on all the CPTs. On the left-hand bottom, you can see where the CPTs were placed, and based on correlations, we take the different lithological units out. And you can see that AA, the artificial material, is approximately the same. That's quite easy. BX didn't change very much, but you can see especially what we were interested in is where exactly is this over-consolidated clay. So having a look at this project and the risk and mitigations following part 2 of Eurocode, and the table below summarizes the risks identified and how these were reduced during different phases of the project. Overall, after making all the CPTs, the identified risks were sufficiently mitigated against by the end of the second phase. And so from the desk study, we have a look at the risk and each individual phase of the fieldwork. We try to reduce this risk up to an acceptable level. Let's have a look at a little bit more complicated project. This project deals with a road underpass. It is geotechnical category 2. In the right-hand corner, you can see the different phases that was envisaged before we started the project. So you see this road in agricultural land. You see houses around it. Of course, next to the road, there's infrastructure, cables, pipelines, ditches, because it's a low-lying area. The first idea was that a sheet pile wall was constructed. We do an excavation, and we build something with concrete, an open tunnel, and that should be about it. Okay, so if you have a look at this plan, an excavation and dewatering within sheet piling, okay. Concrete construction with a pile foundation, yeah. In the vicinity, however, housing with shallow foundations, quite considerable amount of underground infrastructure. At first, the zone of influence was considered to be an approximate radius of about 25 meters surrounding the site, including, however, all adjacent buildings and underground infrastructure. From the desk study, it was concluded that the area has been a polder since at least the early 13th century. Ground level in the area is approximately at 2.25 meters minus sea level. The table summarizes the historic data available for the surroundings and around 250 meters around the site. And so we have some CPTs, we have some boreholes. A lot of the data is from the 1990s, right up to 2011. A site inspection was carried out to check for the condition of the housing, mainly, and for terrain conditions for the soil investigation. Based on the desk study, you see on the right side inset, you can see where the points are. There's boreholes and CPTs, and the red square that I'm pointing out now, that's the envisaged underground crossing. So you see the top layer, Ni, consists of peat, clay, and sometimes fine sands. Then we have the BX, which is fine sands, and the BXCl, which are clay layers within this lithostratigraphic unit. And then we have the EE. The dark one is clay, and the light green one is sand. So for a sheet pile construction with dewatering in the Netherlands, with a top layer of peat and houses just standing right on top of it with a very shallow foundation, this is not a very favorable situation. So we have to address some uncertainties based on this desk study. And what is the thickness and composition of this Holocene top layer? And what's the presence and continuity of clay layers in the Pleistocene deposits? Because if no continuous impermeable layer is present below the site, the zone of influence will have to be enlarged significantly to capture the effects of dewatering. Alternatively, underwater concrete will have to be used, but that means we will probably go way over budget. Based on the desk study, the site investigation proposed was to carry out CPTs in a grid of 25 by 25 meters, to use cable tool percussion boreholes with continuous sampling, and to place a number of piezometers outside the projected perimeter of the sheet piles. For us, it's standard to locate the boreholes at CPT locations, and then we select the borehole locations based on the CPT data, also to allow for an accurate correlation. This is a representative cross-section with results of the accurate CPT correlations. And there you can see that there's the BXCL3, that's a clay layer at around 8-9 meters, and we have a clay layer around 20 meters, which is the EESCL. So this looks far more favorable than that we first imagined. For this project, as it's a CG2 project, we constructed a 3D ground model using IDW interpolation for the top and bottom of each lithostratigraphic unit. It's difficult to show the complete. One of the issues that I have with 3D models is that how to present these properly. So that's why we very often go back to 2D pictures. So if I look at the risk evaluation after phase 1 of the ground investigation, due to the site investigation, the thickness and composition of the Holocene top layers is sufficiently constrained by these issues for this phase of the project. And the present and lateral continuity of Pleistocene layers, clay layers, that the data indicate the presence of several nearly continuous clay layers. So we can go ahead based on this, these results to the next phase of the project. So having gone through the cycle of EC Part 2, and looking at the way we should work in the future, and I'm quite happy. Most of the things are doable for us, but there's also some work in progress for us. And so how to best make and present 3D uncertainties in ground models, for example. And that was mentioned in the previous presentations. Because we're dealing with uncertainties in historic data. There's quite a lot of historic data in national databases for the Netherlands. The uncertainties in correlations. Do we use a standard Robertson, or how does this work out if we do it on a local level? Usually a lot better is our experience. And then, of course, the uncertainties in interpolations. And again, related to these uncertainties and social issues that we have at the moment in reducing CO2 and environmental footprint, what are acceptable uncertainties related to these social issues? Thank you for joining me.
Thank you, Kees-Jan. During your presentation, I got one question from you. Why plan an investigation to a depth less than the vertical ZOE?
Sorry?
The question was, why plan an investigation to a depth less than the vertical ZOE?
That's a good question. Yeah. In this case, the assumption was that the first assumption was 20 meters, and the question is correct. It should have been 25 meters. Good observation.
Okay, thank you. Another question maybe for Sebastiano. It's about Annex F. Why strictly on D, walls reference to strange? I hope I speak it correctly.
Yes. I mean, the thing is that diaphragm walls were considered as representative of all different conditions in which we have deformable earth-retaining structures. So it is stated as diaphragm walls. It could have been stated slightly different as deformable earth-retaining structures, but I mean, it was, I think, for the sake of simplicity, just to identify the category.
Okay, thank you. I will take another question for Marcos. Marcos, it's a lot of text, so I try to read it for you. The question is, please confirm if we are using M2 factors in design approach for rock material. First of all, we have to divide the unconfined shear strength by 1.4. After calculating the shear stress normal stress function according to Hooke-Brown relations, we will again divide the shear strength values by 1.25. So overall, something like 1.4 times 1.25 will be 1.75. Is that a correct assumption from the one who asked these questions?
My reply to that is I don't think so, but I will check and reply in writing.
Okay.
I think it sounds like double factoring to me, but of course I will rather check that. I will say it depends what is the application of the Hooke-Brown model for, but
Okay.
I will try to check that in more detail.
Then I have a question for Sebastiano, or it was asked during the presentation of Sebastiano. There are other types of retaining walls, especially for flexible margin structures.
This is the same as before. I mean, I think it's the same question
okay, yes.
that was detailed.
Mm-hmm. Yeah, okay. Look for another question, this time for Marcos. About improved ground, is it covered by the second generation of Eurocode V2 or in other parts? In part 2 or in other parts?
No, in part 3. In part 3.
Okay.
I mean, like all the other structures. I mean, all the applications are in part 3.
Okay, I go back to Sebastiano. We only have questions during the presentations of Sebastiano and Marcus for this moment. I see another one coming in. Maybe I don't know who can answer that question, but I read it. Not discussed during the presentations, but can you elaborate on how to probabilistic modeling reliability-based engineering will be integrated in Eurocode 7? I guess this was an earlier webinar about probabilistic modeling, so they can check our former webinars then.
Yeah, but I think it's worth repeating that there will be, I did refer to that in my presentation, there will be a specific guide dedicated to answer this question, published by the GRC in the next months.
Okay, thank you. For Sebastiano, probably, if there are any preference towards in situ tests rather than laboratory testing in the new code to avoid issues around sample size, disturbance, etc.
Not in these terms. I mean, there is a clear preference for the direct methods, but there is no preference. I mean, I understand the question that whenever we have to test large volumes, we better go some occasion to in situ test, but this is left to the. I mean, it depends from problem to problem, and therefore it is left to the designer or who is planning the site investigation.
Okay. Going to Marcus. In this unsaturated soil formula for shear strength, there was a mistake. Well, I will answer that. I will take that question back to our task group A1, who checks all those things. So we'll be coming back to that later, I guess. In case of unsaturated soils, should the code also include a requirement to calculate safety for situations where the soil is anyhow saturated, for example, clogged drainage passage, not anticipated raise of groundwater level, etc.?
Well, I think that the question relates to how you define your relevant design situations. Yeah? That is the main point. Yes, you might have cases in which you have design situations in which this is happening, and you might have other cases in which you can conceive a design situation in which unsaturated soil strength is relevant.
Mm-hmm. Okay. Looking at the time, we have about 5 minutes. Sebastiano, why may or shear wave velocity? This is a quite standard practice. I hope you can understand the question.
Yes, I understand. The question is related to the clause in which geophysical methods are presented for small strain, very small strain evaluation of the G0, for in the cyclic and dynamic flows. Actually, this is something that, as Marcos was explaining at the beginning very well, I think that whenever a code is drafted, then there are some adjustments that are related to the to adjust for the sensibility of the different countries. And so initially we started on that clause with a should, as geophysical methods are well established in many countries, but then I mean there was a shift towards a more less strong recommendation and just allow for a may. But I think that it is important that these tests are now explicitly covered in part 2 and hopefully will be used more and more, especially because the shear wave velocity is a parameter that can be obtained indirectly, but it really makes no point to get indirectly something that you can measure directly.
Mm-hmm. Okay, thank you. For Marcus, what was the reason to step back in terminology from angle of shearing resistance, as correctly stated in the actual Eurocode 7, to angle of internal friction, which is just one element of shearing strength?
Well, that was not my recipe.
Okay.
That was another cook.
But in the end, it came into the document. But also that's the thing. I think then a part of getting consensus with each country and everybody.
Yeah, I mean, you need also to consider how sometimes things translate into another languages.
Mm-hmm.
Sometimes people work back into the English draft, translating from their usual expressions in their own languages, and that sometimes results in what you will find odd in the English draft.
Okay, thank you. Do I have some questions left? We have time for 1 or 2 questions before closure. I see here a question about figure F1 of Annex F. Why not in the figure the rigid inclusions?
But okay, rigid inclusions. The thing is that in terms of the formation, I think that who drafted these figures considered that obviously if you have a rigid inclusion, you are going to stay very close to small strain, but I mean this has not been included, considering that maybe it is well known by everybody. But yes, if we should place over there the rigid inclusion, we would stay very close to the very small strain.
If I may add something here, Gert, is that
Yeah, of course.
we're in the process of starting discussing the national annex in Spain, and this annex is an NDP, and there were questions about that, and probably we will enrich the figures, adding some extra information. That is a possibility that is so.
Yes, indeed. If it's an NDP, every country can take it up and improve it for their country specifically. So yes. Okay, I take one last question. I see a question in the Q&A. In heat, and don't know for whom I expect. I think maybe for Hakan to close. In heterogeneous vertical and horizontal geologic formations, in the uncertainty is huge. How to deal with uncertainty, essentially in probabilistic approaches?
First of all, you need to know the size of the uncertainties. If you don't have an idea of the distribution vertically versus horizontally, you can only guess, because it's a very open and a very tricky question. So it's very hard to give a direct answer that how to do it. It depends on the geology, if it's soil, if it's rock, whatever it is, and where it is, and also the water and pressure condition, etc. So, but you have to take into account the uncertainties, and that's maybe as a closing remark. You are not more certain than you are about your uncertainties.
Thank you, Hakan. Then I think it's time to close the webinar. I will thank all attendees and subscribers to keep with us during the webinar. And I hope we will see each other next webinar in March 2024. And I want to thank all the presenters for the expertise and lending their expertise to us as attendees looking at it. And so I will thank everybody, and we will see you next time.
Bye.
Bye bye.
Bye.